Okay, well thank you all for coming to this, what I shall call, grandly, the inaugural Cambridge NetKernel Users Group, which comprises Chris at the moment, I think, so maybe Kim as well. So I'm going to basically, for those who've not played with NetKernel or seen NetKernel, I'm going to introduce the concepts behind it and try and explain why on earth we took this crazy kind of journey. And then hopefully by showing you some demos and giving you some rich examples of what happens when you do this, you'll see that it hopefully wasn't such a crazy idea after all. And let's keep it interactive. There's a small gathering. If you've got questions, we can take those questions online. But there's quite a lot to cover, and I want to give you a good sense of the stuff. So let's get started. So I'm going to give you some background. I'm going to tell you what this concept of being resource-oriented means, some of the principles and building blocks that go into that, some of the strange consequences on performance that you might not anticipate when you look at this, what it does to architecture, and then realizing that there's no actual limit to this abstraction, that you can break out of the box and use it. This is the background. This is really for historical record, because we've actually been doing this for a hell of a long time. And my background is that I'm actually not a software person by training. I'm a physicist. And I joined HP research labs after finishing my PhD in '95. And like all physicists who kind of fail at doing physics, they start getting sucked into doing software, right? Because it's like, I can control the whole universe with software. I don't have to wait for the physics to tell me how it works. And I started to get drawn into building and trying to research very, very large-scale systems. I wanted to build complex transactional architectures, and they were all obviously internet-based, because the internet was a given. It was understood that was the fabric for the information systems. And what I was armed with was the state-of-the-art of modern software technology. So I had object-oriented frameworks, I had early generations of J2EE enterprise stuff, all this stuff, and you're thinking, this is the state-of-the-art. So why the hell is it everything I build falls apart and becomes brittle? Why is that? And I, being maybe arrogant, I didn't look to myself and think, it's me failing. I kept looking at the tools and thinking, this can't be this hard, it can't be this difficult. Why is it that I can build something to a certain level, and yet eventually it gets so grungy that you have to throw it away? And what I started to realize was, talking around inside HP, was this is actually how software was done. People do throw things away. That's what happens. It gets to a certain stage and you start again. And I was looking at it and thinking, this is insane. The economics of the system just don't stack up. And yet, outside, over there in the real world, is this thing called the web. And the web is just growing. It's growing exponentially. Clearly, its economics are somehow different to what we're doing inside software. And that gave me, basically a focus for research. It basically said, look, if you can work out the fundamentals of how the web works and extract the essence of that, then maybe you can start to bring that down to the small scale, down to how you put software systems together. And so I started researching and built a small team, and we started to do basically what now is called REST, but at the time didn't have a name because we were inside a corporate place trying to work out how the web works. And one of the advantages I had is that I didn't look at it from the point of view of the software system. I looked at it from the point of view of what my training was, which was quantum mechanics and state and measurement and how systems behave under those forces. And so I looked at the web and thought, you know what it is? It's just a great big state space. It's just a measurable state space where each location in the state space is an eigenvalue. You can measure the system and get a representation of that state back. So it kind of was a very natural system to look at for me. But I wasn't satisfied in just kind of working out what REST was. as I said, what I wanted was to take the principles and then bring them to home, to keep them general, which is kind of what physicists' disease is, that they always want to generalize when they find a specific. So I was looking to generalize what was happening in the web and then have an abstraction for it. For reasons I can't go into, what happened around the late turn of the millennia, 2000, 2001, HP sort of moved out of its middleware position, which left me with a bunch of ideas and no real place to use them, no place to deliver them. So what I did was I spun out and started a startup called 1060 Research. And the basis of this was quite ambitious. We were research first and development second. We needed to still, put in place the concrete stuff behind this. But during that early phase, what we did was we started to create this product called NetKernel, this implementation of the abstraction. And over the years, we've matured both the technology and the abstraction. And the problem, or rather not the problem, but the requirement was that we needed to be patient. There was no point in us trying to jump the gun and trying to describe this too soon, because actually the general awareness of the concepts behind the web just hadn't matured yet, that people weren't conscious of what it is they were doing in the web and how the web was working. And it was just too big a proposition for us to boil the ocean and try and educate them. So what we've done is we picked off early adopters in particular sectors and used those as the basis to validate and mature the technology, but without trying to necessarily broadcast and advertise this thing as, hey, this thing is around and usable. And what happened around 2008-09, you'll know, is that there was a general awareness of REST starting to grow. And now people, if you say REST, they'll probably at least acknowledge it. They're probably not applying it. They probably don't fully embrace and understand what it's about, but at least it'll resonate with them. And that now gives us a toehold to actually talk about the principles beyond REST. If you can understand the concepts of REST, then now we can start to talk about the basis behind it. And we're getting to that point where we're starting to get into a more mature market, and that means we can actually talk to people about this stuff. And one of the signs of that is that imminently there's going to be a book called Resource Oriented Computing in NetKernel from O'Reilly coming out. And so that's, again, one of these validations that there's now sufficient interest and knowledge in this area that it's worth having books and evidence. So what I want to do is tell you about what it is. And the simplest way to do this is if at the end of this talk, if you ever need, this diagram basically summarizes and is the only thing you really need to know about in ROC. This is the whole of it in one abstraction. And I'm going to describe this diagram two ways. The first way is something you know, because some of you are much younger than me, and you've been born and raised to use web browsers, and you kind of don't even know that you didn't know how to use a web browser. I remember learning to use web browsers, things like that. So I'm going to talk about it from the point of view of the web, which you know and interact with daily. And then I'm going to talk about it from the point of view of ROC, which is a complementary extension. So what you have in the web is you have this thing called a requester, which is a browser. People think of it as a web browser. And what happens in a web browser is some external event happens to cause it to want some new information from the web. It's either a user clicking a link, or it's them typing in a URL in a box, or it's an AJAX script timing out and making a sub request for resources, whatever it is. But an event happens. When that event happens, an identifier for the resource is constructed or available, and we call those URLs. And the URL, what happens is that the browser effectively interacts with this global space, this World Wide Web. And this space contains the resolvable set of all possible information that you can obtain. So you can think about this space as basically being the set of all identifiers beginning with HTTP, HTTPS, right? Because that's what an HTTP URL is going to resolve. And obviously inside here is at a small point in the space is something like Google.com. Another space there might be Facebook. Other spaces there's various sets and parts of this global set have a certain part of the address space that they resolve to. And what a browser does is a browser effectively, its contract with the space is that it starts talking to DNS. DNS is the resolution mechanism behind the space. And the requester looks for the host name part of the URL and then resolves and finds some physical network socket where it can actually knock on the door and say, hey, I want this piece of information. So what it does is it resolves and finds some physical endpoint, physical point in the network. And what it actually does is it literally knocks on the socket and shoves the request in the door and says, look, I need this identifier. It actually passes the identifier to the endpoint. And the endpoint then is basically left to decide, what does it mean? What does that? There is no semantics in that. It's literally just an opaque token that's been passed in the system. So the endpoint now has to decide, what do I do to fulfill that request? And obviously, we call this endpoint a web server on the web. And the web server, the first web server basically mapped it to a file system. That was what Tim Berners-Lee did with his first generation one. And then you had CGI, and now you have all these object-oriented frameworks for web interactions. But effectively, they're all doing the same thing. They're basically receiving a request for an identifier, and then they're doing something in order to construct some state, to say, here is the state of that identifier that you requested. And having constructed it or computed it, they return that state in a form that's called a representation. And the representation gets transferred back to the requester, and then the measurement has been made. The requester has got some value from this space. And of course, the reason it's called a representation is because, in a sense, the space is always logical. It's always actually abstract. You're basically always saying, this space will always give me Google.com. That abstract resource is always there in that space. But it's only when you measure and make a request into that system does it collapse down to a representation. See how it starts to feel a bit like quantum mechanics? That's what happens in quantum mechanics systems. You don't get any values out of the system, but all possible states are there until you apply some action, some measurement on it. So that's how REST works. And of course, why is this a good model economically? It's a good model because fundamentally there is no physical coupling between the requester and the endpoint. And that means that this technology, whatever it might be, can evolve at its rate of change. This technology can evolve at its rate of change. And when those events need to be satisfied, they can be resolved and coupled momentarily, just for the period of that interaction. Why else is it good? Well, there's no physical connection. There's never ever a physical connection between the request and the endpoint. Not in the sense of the system. There's obviously an internet sockets and so on in the background of the internet. But what happens is the request is logically resolved to a socket, but that can be load balanced out across as many physical endpoints as you need to satisfy that thing. So one logical request can be matched to as many physical servers as you want. So you can scale out as demand grows for that particular URL. So, for example, Facebook, Google, they all started on one server at one point in time. Now they run on tens of thousands, hundreds of thousands, millions of servers potentially. Nobody noticed, nobody cared. Nobody needs to care because the logical resource is still there. The logical identifier is still there. That's where I'm talking about this economic property of the web coming in. And this is where I wanted to get in terms of software systems. And so there's one other important property, which is the requester and the endpoint. The requester actually has no interest in executing or making this endpoint work. It doesn't want that endpoint to run code. That's not the contract in the web. The requester wants some information. It wants state. It wants a measurement in the system. It wants a representation of the state of the system. It doesn't matter whether you run code or not. So the requester, if it's previously requested that same thing, can obviously have a local cache copy that it doesn't care. It can use that copy. Or, as you leave your local space, you can put in a local edge proxy in server into your system and say, well, actually, all of you locally are asking for the same resource. I don't need to go out to the world to find it. We've already got that, so I can use it here. Or you can put proxies in like Akamai and these CDN networks where they basically say, we don't even need to send you across the network because we've already got a copy for you anyway. Or you can put one in front of this tier. So what you can do is you get multiple chances to avoid doing work. And being lazy as I am, I love having multiple choices not to work. That's very desirable. So it's almost, to me, it's almost like a defeat in the web if the request ever actually gets to the endpoint and has to run code. It's almost like you've lost. The objective of an architect is to try and do whatever they can to avoid that having to happen. And then, of course, you get into the problem of reality. But we'll get into that in a minute. So that's how the web works. That's what REST is, fundamentally. Now let me tell you about resource-oriented computing. So resource-oriented computing says you can have a requester. That requester isn't necessarily a browser. It's basically a component, a piece of code, something. And that piece of code is fired through some event somehow. Something happens, whether it's a method call or an external socket, or whatever it is, it doesn't matter. But that event happens. And in order to satisfy that event, we don't say, I need to run code. What we say is, I wonder if I can think of an identifier for the information that would satisfy this event. Can I construct an identifier for the information that would satisfy the event? And this requester sits in an address space, and that address space provides a resolvable set of resources, a set of logical names for information that could be potentially useful to this endpoint. And the request gets issued, and it gets mediated, and eventually, if it doesn't find it on the way, it gets mediated and issued to the endpoint. Just like in the web, the endpoint actually receives the identifier, the information identifier, and says, please sort it out. There's no semantics in this information, it's a token. It just so happens that this space has determined that you should handle this. You are responsible for this information. So the endpoint looks at the request, does whatever it needs to do, adds value, computes something, turns back state to requester. Okay? Now the difference between this and the web is the web has one space. In fact, the W3C has worked very hard to make sure it is one consistent address space. That's their raison d'etre of the W3C, is to ensure that consistency. In RC, we're saying, do you know what? Why leave it at one space? Why don't we have as many spaces as we need to solve our problems? Why don't we use spaces as the unit of architecture in which we solve problems? And we can create relationships between spaces. And those relationships are mediated by endpoints. Everything is essentially the same logical component. And do you know what? Something else. Why do we leave the space when we hit an endpoint? Why don't we say that this endpoint is just actually receiving an event, just like any other thing? And if it receives an event for a request, it can issue more requests. It can say, well, I need more information in order to satisfy this. So rather than the endpoint, the web server being an exit route off the web, why don't we say, well, it's an on-and off ramp. It can go back into the web. It can make more requests and more information. So that's the generalization. That's saying, look, we can take this web idea further. We can liberate ourselves from a single space, and we don't have to leave it. We can carry on being in it if we want to. And as I said, the basic idea is that there is no connection between these pieces of code at all. Only when an event triggers the resolution and execution. And just like in the web, that is a transient relationship that happens in some time. So this requester and this endpoint can evolve their own rates. There's no coupling at all. It's a zero coupling system. It's a transiently coupled system. So those are the basic ideas. Can you pull it off is the big question. Can you make that thing work? So I've got a demo now. And what I've got here, I've got an address space. Here's a diagram. Here's my demo address space, right? And I've got some endpoints, resolvable endpoints in this address space, okay? And I've actually got some endpoints that know about other address spaces, just to show that you can have relationships between spaces as well. But we don't need to worry about that too much. What you have to imagine in the demo is, when I type these identifiers, if I was showing you Java circa 1995, 1994, this demo I'm about to do would be like me handcrafting bytecode and saying, isn't that cool, I can write bytecode? And you'd be going, you're an idiot. Don't write bytecode, that's a crazy way of doing things. So you're going to think I'm an idiot. But what I'm doing is I want to show you that the fundamental stuff inside, really does work, really happens. And then show you why it happens. And then show you what the properties of these identifiers, how they take on a value as well. So I'm basically going to, the way I've got this set up is I've got a demo, it looks like a web form. The only reason I'm using a web browser is, web browsers are great at showing you representations when they come back, because they're capable of dealing with MIME types and representational rendering. So that's what I'm doing. I've hooked this web surface, but when I type a request in here, what it does is it just issues that request into that address space. That's what I've got set up here. So forget that this is a web application. It's not a web application. I'm showing you direct injection of requests. It's resource-oriented bytecode. So what do you do when you need to, what do you do when you want to invent this system? Well, you don't reinvent the wheel. Okay, the URL turns out to be a very nice, very flexible, very easily parsed, very well understood identifier structure. So we're not going to reinvent that wheel. We're going to use URLs, but actually the general term for URL you'll know is a URI, Uniform Resource Identifier. And URI is a very well-defined uniform specification for identity. So we'll use the same scheme, right? We'll use URIs inside our system. Don't need to reinvent them. And you'll know that a URI consists of basically two parts. There's something that's the scheme, the bit that's the prefix that says this is the mechanism we'll use, or the core fundamental set that we're working with, like HTTP. But because we're inside, we don't use HTTP, right? Because that's an external identifier. That's saying I'm going to use the hypertext transfer protocol to go between these systems. So we couldn't use that. So we just said, well, let's just come up with a name for an abstract set of resources. Let's just call it res for resource. It's abstract. It's not embodied in any protocol. It's purely an abstraction. So when you see res, what that means is we're not using physical level resources. We're using internal, logical, abstraction resources. So what I have here is a resource identifier for hello.text, right? And if I issue that request, what you get back, if my browser is connected to my system eventually, is hello. I get something back. So there is, in my space, there is the logical resource whose identity is hello.text. And when I request it, the request goes through the space, finds some point that says, yeah, I can give you that. I can give you that resource. And I get back the representation of that resource. So what else have I got in my space? Well, what if I had the whole of the World Wide Web in my space? What if I just tricked my space and said, you know what, I can mount the whole World Wide Web and put all of those resources in as well. So I'll have all of HTTP and I'll have hello there. So I've got a bigger space than the web inside here. So if I issue a request for that, this is going over my phone, so this may be slow. It may not even work at all. But it does eventually work. So when I make a request for HTTP there, what happened was it went into my space. My space contains an endpoint that promises to give me all the resources that begin with HTTP colon. And if I ask for one of those, it actually acts like a client and goes out and makes requests for HTTP resources and brings it back in. So I've effectively I've mounted the whole of the World Wide Web and put it into another address space here. And so I can ask for all those resources in my space. Now that's all very good, right? Asking for a static resource is like a really terrible demo. How do I make things do things to other things? Because that's what software does, right? Things happen when you ask things to work against other stuff. So I reckon you can probably read that as a sentence, but this is the first example of this scheme called active. And active is an IETF scheme that we published to explain how to create rich structures for identifiers, but they're still URIs, And the way to read an active URI is it always begins with active. It's got some base part that basically says, you know, this is the primary location for this resource. And then it has this plus at delimiter mechanism. So a plus means here's an argument, here's something I want you to know about. And its name is, in this case, operand. And the at is saying the named thing is this URI. It's another resource. So it's a way of delimiting and specifying multiple resources and referencing them with names rather than sending them as direct positional locations. So don't worry about operand. I'll explain that in a minute. But what you can see is, you won't be surprised that that's going to return me back the uppercase of that resource that I just showed you. So I get hello there back. Okay. But because that's just a resource, and it's one of the resources in my address space, and I can say hello. It's going to take a second to get it from Google again. There's the uppercase of Google, right? That's useful, maybe a useful resource to somebody, I don't know, perhaps. So, now I can take this further. Now I've got this addressing scheme. I can start to think about software services this way as well. So here I've got an XSLT transform engine. And I've got, if you look here, it turns out my address space contains some really crappy data, resdata.xml. And it's rubbish XML, like it's a data item with an attribute name for a color, and then inside a color value, okay? But what I've got here is a service or a software endpoint whose responds to XSLT. It expects an operand, the thing that is to be transformed by the XSLT, and it expects an operator, the thing that's going to apply the transformation, the thing is the transform that's going to be applied. In this case, I've got a stupid transform as well. And when I apply that, what I get back is a color HTML version of that data, the transformation of that data. Now, because each one of these resources, you know, there's an example of going out to the web, because I can transform something that's outside. Because it's not outside. That web resource is inside my address space. Logically, it's in my address space. So there's a piece of data came in from the outside world applied through the same transformation. Because each one of these arguments is just another identifier, and there's nothing that stops you saying, well, why can't it be another active identifier? Of course, it can. So what I've got here, I told you this is bytecode, right? This is escaped, because it has to be, because it's inside. It's an argument already. So let me just unescape it, just to prove what we've got here. What we've got is a filter. We're selecting the green from the data. So if I issue a request for that, I get that data back with just the green part, okay, just that resource. So now you'll be able to read that. That's basically saying, there's the green bit. That's the resource I want you to transform with that transform. So what I get back with that is the green bit, the green resource. And of course, here's the crazy thing, right? I'm writing this awful way to code, right? This is starting to get very complicated. But you've got to understand that identifier is both the description of the resource that you want to obtain from the space. It uniquely defines, in this space, it uniquely defines the transformation of that data by that transform. So that is the name of that transformation. That is the name of the resource that I get when I do that. So the next time I request it, what I get back is the same resource. Because there's no point in running code, is there? We've already done that. I know what the identity of that resource is going to give me, and it's not going to change. In fact, it's never going to change. As long as the system is ever not touched, it's never ever going to change. So I don't need to do anything. I can just give you that resource every single time. And the same is true of all of these resources that I'm showing you. They all are unchanged. There's the green box. That doesn't change. And of course, that's a terrible name for it. And I can't give that to somebody else to use, the green box. But I can always call it something different. Why don't I call it green box? And abstract it again, so I can call that something useful. And when someone makes a request to green box, it actually makes a request to that other thing. But they both are the same identity. They're both the same resource. A resource can have any number of names. That's what I'm saying. So green box and that other one are just as valid. So if I issue a request for green box, I get green box. Doesn't matter to me. So these are the basic primitive ideas behind this. And as I said, what I'm doing is I'm doing this at a really low level. And you don't do this stuff by hand. But I'm just doing these tricks to show you that you can do it by hand if you want to. So let's get back on the story. This little demo that I had was really rubbish. It had this two-upper thing in, it imported some resources that were just basically mapped to a file system, just like the first version of the web. It's got a Fibonacci thing in there as well. And that's the HTTP, so it's a really poor little demo. But the point about having these spaces is these are the units in which you can compose your application, compose your architecture. So rather than thinking about code being linked to code and making relationships there, we start to move up in scale. We start to build systems with bigger lumps. We're building stuff with, the whole set of the web. Here, you want the whole set of the web? There you go. That's a very simple thing to give to somebody. And what you end up doing is you end up focusing on very small units that contain really quite simple capabilities, quite simple functionality. And then that functionality starts to grow and become complex through simple relationships. So what I'm showing you here, I'll show you it for real, is my NetKernel system. Because NetKernel is built out of all these spaces. It's got hundreds, thousands of these spaces in it. And each one of those spaces does a particular thing. But in aggregate, it becomes my emergent system, my complex system. So here is, this is actually a view of this tool. Okay, so I'm using the tool to view itself through this thing. You see that I've actually here, I've got a connection coming in from the outside world. That's actually an HTTP transport. So this is, I'm making real web requests now to my real NetKernel system, and they're arriving in on that channel there. And then it's going down through some spaces and things are happening. And if we go a bit deeper, we start to see that there's other layers and other bits and pieces happening down here, and then we get deeper and deeper and deeper. And these diagrams get bigger and bigger and bigger. And I'm not going to get it all on screen, but you start to see that you start to see emergent patterns in the architecture. And that's because you're no longer working at the code level, you're working purely at the architectural level. You're actually sculpting and combining and creating relationships between architectural features. And you have these abilities to control these things. And the relationship between these things is this simple, just like I showed you with those endpoints. Events, something happens at this point which causes it to issue a request, which causes it to be coupled to this space. But that space and that space don't know anything about each other. They're not coupled. They just have a transient relationship once that request arrives. Okay. So my entire software system is a completely loose federation. Let me go down. If I scale it down so you can see it properly. My entire software system is a loose federation of completely decoupled spaces. There's no physical coupling there at all. I just happen to be able to follow the relationships down and find out what paths would happen if events would happen. Okay? And what that means is I can hot swap any part of it in real time because there's no physical coupling. So I can take any bit of it out and I can replace it with any other bit alternatively in real time and just have the system adapt to that new change of relationship. So what that means is that my software is no longer linked. I can evolve it progressively over time. I'm no longer having to reach the precipice in my architecture and say, oh, we can't do any more and throw it away and start again. I can basically say any one piece of it, just like the web has evolved from its first origin through to now, with nobody ever throwing it away in between. The same thing happens in your software architecture now. So you can do this. And inside these boxes, if you're worried about where the code's gone, well, effectively inside each one of these boxes is a little tiny object container. That's where you leave the logical world of ROC and go down back into physical code if you need to, if you want to. All right, this is a long, drawn-out kind of story. But what I wanted to show you was that this basic building block, this basic idea of, let's take the web, which is a single address space, and let's generalize it, actually really can be made to happen, because you can build webs and webs and webs and webs as fine as you want. So then what happens? So what I'm basically saying is that two-phase computation is a better model from the point of view of the economics of the system. That's what the web is. The web is a two-phase computation model. First is the resolution phase, where the browser works out where it goes and asks for the information. And the second is the computation, execution phase, where the request actually arrives at an endpoint. And you look at that and you go, God, that's going to suck. It's going to be a terrible way of building a system, right? Because I'm going to do twice as much work, and this surely, if I link the code, link the system together, that's got to be the fastest route to solve the problem, hasn't it? Because that's what we're already taught. That's what coding is about, right? Well, some surprising stuff happens. First and foremost, by decoupling these two phases and saying, I don't actually care about where that endpoint executes or how that endpoint executes, and I can do the same trick as you do outside with the web. I can load balance inside. I can basically say, you know what? I can assign those requests to different cores in my system because I've got multi-core architectures now. So I can basically load balance across multi-core, which means that as my demand grows in the system, or as I add more cores to the system, it's going to scale linearly with that new compute capability. So just like Google started on one server and now runs on millions, well, you can start on a single core machine, and if you need it to run more, you just put it on multi-core, multi-core, multi-core. So if you go into these 512 core architectures that are going to be around the corner, or 1024 core architectures, how are you going to make your software run on a 1024 architecture if you're tightly binding it together? It ain't going to work, because you just can't deal with the complexity of that. You've got too many degrees of freedom to worry about. But if you load balance inside by decoupling it completely, it'll just use it. It just takes the capability on. So it turns out that actually these systems start to run better, they run faster when you get to larger stored core systems. But there's something else happens as well. There's something really very interesting happens that we didn't really expect. And that is, because every single thing that you request has an opaque token, has an identifier associated with it, then you can hold on to everything. Everything's got a label, everything's got an identity. So you literally can hold on to everything. So what that means is that you can not just guess about putting a caching layer into your software at some point between an API and some other part of the API and saying, look, that's probably the best point to hold state and reuse it. We just say, well, we don't actually know, and the system is dynamic and it's adapting to the outside world, and it's in dynamic equilibrium, and it's a distribution of state. Let's hold on to everything and find what's the most useful state and reuse it as necessary. So we cache everything, and we cache it not in one dimension, but every dimension simultaneously. We cache it at every boundary in the system, the single points, the composites, the aggregates, the transformations, and so on and so on. And if you find you need that transformation, then obviously that's the thing you'll hit the cache for. And eventually we start to throw away stuff that isn't used as much because you haven't got an infinite amount of storage. And the reason caching works ever, is because the real world, back to physics, the real world behaves physically, and physical systems have natural statistical distributions in them. You know, I'm not suddenly going to jump from this chair to that chair. It's possible, but I'm not going to. Right? It would be a big surprise. But there's a very good chance that I'm going to move to the next slide in this presentation, you know, or go back to the previous slide in the presentation and talk about something else. That's quite high probability, you know. So there's a natural statistical distribution on this state in my system here. And that's just how the real world is. So you look at banking apps, or you look at information systems, or you look at whatever you do. The interaction of the user with that system naturally creates a context and a statistical distribution around the information they're going to work with that starts to make it more likely that they're going to reuse parts of it again. You know? So your little profile that comes up on a web page or whatever, the next page you look at, you want the same piece of information. Like, why recompute it? That's a stupid thing to do. We know that it's going to be recompute. But if we identify it as a resource, we don't even need to think about caching it. It's just there. And then there's something else you can do. The web does its best to cache, and is actually quite effective, and it tries to mitigate the network transfer cost by putting caches at every layer. And it does a pretty good job. But as soon as that representation is released and left in the wild, the only thing the endpoint can do to it is say, you know what, don't come back to me within X amount of time. It can basically say, there is a time validity on this representation that will be sufficient for you to hold on to it for a bit. So it puts in these cache directives that are basically time-based directives. But we're not in the web. We're inside software. And what we know is, not only can you do time-based directives on the exploration of this stuff, you can hold on to it for amounts of time if you want to. We know that whenever a request is made, we also know that it causes a cascade of other requests or other pieces of information all the way through our architecture. And the system knows about this because the system is the mediation for those requests. It mediates all those requests. So why don't you accumulate knowledge about all of those requests as well? What about saying we can create a dependency model? We can dynamically find and discover for any resource you ask for, we can know, truly know, everything else that would be required to compute that. And if all those other things haven't changed, then we can serve this. But if any of them do change, then obviously some things happen in the system, some event elsewhere in the systems happen, and therefore I need to recompute. So what we can do is we can have cache coherency through a dependency model that's discovered. And let's show you what the effect of doing that is. I'm going to show you the dependency model, but then I'm going to kind of show you that there's something really interesting happens as well. So let me just show you the dependency model first. So what I've got here, somewhere, if I can find it, is a very simple demo. And I'm going to show you some code. I'm going to show you how you write code in the system as well. What I've got is a resource. And when I ask for that resource, let me show you the detail of it first. Where is it here? When I ask for this resource, res demo GT, what I've got here is something called a mapper. And a mapper is that way I did that alias for the green box earlier. It basically says, if you ask for that, actually ask for that. It's a way of putting in multiple names for resources. So I'm basically saying, if you ask for that, ask for that. And this is index.html. And index.html is that page I saw on the outside. Oh, I've got some, sorry. I've got to hide these things. You didn't see this, right? And if I ask for that composite resource, what I actually ask for is this resource. Active XRL2, what the hell's that? Plus template app, res scripts composite XML, plus mime type app at text HTML. What's that? Well, let's make a guess. This is some kind of thing we've never met before, but it looks a bit like the XSLT thing I showed you earlier. And that's a template, right? So let's go and look at the template. The template looks like it's called res scripts composite XML. What's that? Well, res scripts composite XML is this file here. Oh god, you didn't see that either. Let's do this. Sorry about that. Composite resource, right? And what composite resource is, look, it's a piece of XML, right? But this is an XML that contains within it, it's not an off-ramp. It's an off-ramp back to an on-ramp. Contains a set of references to more resources. So it's going to, when that XRL2 engine is given this template, it's going to go and look at each of these references and say, well, that's another resource. I'll make a request for that. I'll make a request for that. I'll make a request for that. And look, each one of these is actually just 1, 2, 3, 4. So there's a set of 4 resources. Now look, if I request it again, you notice every time I request it, nothing happens. Because actually what I'm doing is I'm hitting the cache every time. Because why bother doing anything? Nothing's changed in the system. The system's telling me nothing's changed, so why bother running it? So let's look at each one of these individual resources, right? How are they working? Well, let's look at this module XML. We've got this thing called the way you map infinite sets of resources down to an endpoint is you have to come up with some pattern match, right? Because you're making identifiers, and you want those identifiers to go and be resolved to a single endpoint eventually. And what we have is this technology inside NetKernel called grammars. And grammars are basically a very rich expression languages for matching and resolving request identifiers. This is a very rich one, and it's got a base part, demo GT res, and then here is an integer with a regex match. This is a quite complex grammar, but there's much simpler ways of writing these things as well. But if a request for that resource happens, then it's going to issue a request to, hey, it's going to call active groovy. A bit like XSLT, isn't it? One of these services. What's it going to do? Well, it's going to be given an identifier to its resource that it's going to execute, and its resource is this thing called operator, res scripts, res.gy. And also, we're going to relay through that identifier of the argument that we extracted off here. So we're going to construct a new request to Groovy, pass it a script reference, and relay the I value that we just grabbed. So let's go and look at res.gy. And this is a really hideous piece of code, but that's because I wanted to put it all in one box and just do a bunch of mungy stuff in one place. What I'm doing is, like every endpoint, the endpoint goes through 5 steps, right? Every web server goes through these 5 steps, whether you noticed it or not. The very first thing a web server does is go, what do you want? Because the request comes into you, and you have to work out what the request is for. So this is saying, there's a context object that NetKernel's providing, and the context is the sort of root to an API that says, get the request. I'm going to say, what do you want by looking at the request? And from that, I'm going to say, give me the argument value of I. So what is the identifier of I, the I part of the address that you've been given? So that gives me I. Now I'm going to do a little bit of stupid Java, new date. Now the reason I want a date is I want to change the color, or I want to put the date into this little fragment of HTML. And then I want to compute a color value here and put that color value into the border so that when you see it, you get a visual view of when it was computed. So it's got a date timestamp in it, but it's also got a color based upon that timestamp. So each one of these was actually generated at exactly the same time. But you notice they've each got a different I. So there was 4 requests made for 1, 2, 3, and 4. So they all got. So what happens if I edit this script? What if I say Cambridge, change the resource? So the script is a dependency of that resource because it's referenced as a resource, as an identifier on that request. So now, if I re-request it, they all updated because the dependency model changed. Because the dependency that was associated with that tree physically changed. There was a physical change to a file. So now I can't hit the cache. I've got to do something. So I'm doing more than time-based expiry. I'm doing dependency-based expiry of the resource. You see they're now expired at 1930. Now here's the bit that blows your mind. When you're inside one system, it's pretty crap that you can only depend on the internal state of that one system, because the real world depends upon multiple layers. You might be the front tier, you might be the middle tier, you might be the data tier, there might be a database being changed externally, there might be all sorts of events happening outside you in the outside world. So it's not sufficient that you just measure and detect internal changes of state. That's no good to you. It only gets you so far. You're just a little bit better than the web with its time-based dependency. But what if you could take this dependency model, and instead of just thinking of depending on real resources like that file I just showed you, what if we could imagine that we could depend on imaginary resources? Right. So this is like if you've ever done any engineering maths, you know that you spend all this time in school and they teach you about the real number line and you do all this addition and stuff. And then as soon as you go to engineering, they say, there's this imaginary set of numbers over here that no one ever told you about. And there they are, these imaginary numbers. And if we use those imaginary numbers, things get really simple. We can solve problems in a much easier way. Wow, that's pretty amazing. Well, I'm here to tell you that the web deals with real resources. And NetKernel can deal with real resources too. But just like real resources, just like engineering, we can imagine imaginary resources too, and we can depend on imaginary resources, and we can share those dependencies between systems that aren't even related. They have no connection, other than they all agree that they depend on the same imaginary resource. What the hell is he going on about? I can see you saying. Well, this is a way of attaching and this is a way of making a declaration that says, I want to depend on some imaginary resources. These don't exist, these will never exist. If I make a request for them, I won't get anything because they're imaginary. But I'm still going to say I want to depend on them. And we call this pattern the golden thread. And the reason for that is we think of these resources as basically being associations, threads of association, golden threads of association between other resources. And what I'm going to do is I'm going to say I depend on virtual resource I, where I is that value I plucked off the request. So I'm going to have one for every one of my resources. So I'm going to depend upon virtual resource 1, 2, 3, 4, whatever it may be. But also, I'm going to say that every single resource depends upon virtual resource all. And then, just for the hell of it, I'm going to take the modulo of that integer and say, if you're even, you depend on even resource, and if you're odd, you depend on odd resource, right? And then I return my response. So what I've done is I've made a physical set of associations to this resource, and I've created a set of logical virtual associations to this resource at the same time when I computed it. So now, what happens if I expire virtual resource 1? So just virtual resource 1 is now expired. You know exactly what's going to happen. Virtual resource 1 was expired. So the next time I asked for that composite of the resources, the top one had to be recomputed because it couldn't possibly be used. We worked that out from the dependency association. So let's take out all the other ones just for the sake of it. So now you can't see the color very well. Let's do that again. The timing was bad on that one. Sometimes you get the same color, of course. Well, there we took out the even, we took out the odd ones. Long ago. And of course, you know what happens if you cut all of them. They all just line up again. So I get them all back on track. So what I can do is, I can in my architecture start to take control of the state of the system and make approximations for reality, because reality is changing all the time around us. And the reason you cache stuff is to say, look, this is good. Well, the reason you put a time expiry on something is you say, this is good for a period of time. And in future, it'll be good enough for this amount of time. But what we can do here is say, it's good enough for all time until we decide it's not good enough. and then we can kill it, and we can poke it out of the system. So we can have external systems, we can have architectures where we build predominantly read architectures, where most of our stuff is building composite views across sets of resources and presenting them up in services or whatever. And then we can have, because most systems are read more than write, and that's just the nature of the world, we can have other channels that come in which state changes, and when that state is changed, we can then cause the read side to renormalize itself, rejig itself, based upon these virtual associations, without having any physical code related to these things. The only thing that has to be shared is the same algorithm for how they decide what their view of virtual resources are. So that's what happens with Golden with this thing. So this really weird thing happens. Okay, this crazy idea of completely decoupling your software starts to go faster. It starts to be a faster way of doing the solution because it scales on these multi-core architectures without any problem. But you start to find that invariably, in many cases, you didn't need to compute it at all, but you just didn't realize because it was a piece of knowledge trapped way down inside some relationship that you wouldn't have ever discovered by analyzing it. And you certainly wouldn't have been able to put one piece of caching around that individual part. So what we're doing in computer science terms, there's something, this is a long, taking a function and holding on to its values and reusing them the next time is called memoization on a function. It's what, or lookup, you guys who do image processing, about lookup tables and shortcutting things. What we're doing is we're saying, let's generalize that. Why don't we systemically memorize everything, hold on to all state, and discover how valuable it is. And it turns out that often large parts of information is valuable. And even if you do have to recompute it, it's still a relatively small part of the whole set of stuff that you have to recompute. You only recompute the very smallest subset all the time. Okay, last part of the demo. If you started thinking this way, and you started to build internal parts of your system this way, and you realize that you can put all this stuff together inside an architecture, inside one physical server, you then start to say, wow, wouldn't it be great if I didn't care where any of those spaces lived? Maybe I can take the abstraction and make it just work anywhere, between anything. And of course, going back, this is almost like going full circle, because this is saying, well, of course you can do that. You can use HTTP. You can make requests out into the web and have services come back. But you can see that HTTP in the web is only a partial story. It's only half of the picture. It's not the full story. What we want to do is take this ROC abstraction and make that work across devices as well. So that's this last part. So what I've got here is, a demo. And what I've got in this demo is, this is going to be pretty slow because I'm running it on damp string on my phone, to damp string on the other end as well. But I've got a little local demo here that'll be a bit faster. And what I've got is an image, okay? And I've split the image computation, and I've said that actually each rectangle of this image is actually just a resource. It's a set of points in the Mandelbrot set, okay? And I've split that set up, and I've said there's a service called Active Mandelbrot, and I can ask for a subset and say, give me a little bit of that thing, and give me the view of it. And every time I click on this view, I'm able to ask for another subset, another set of view. And I can keep zooming in, arbitrarily down into this click it, inside this view. So I can explore the Mandelbrot set, because the Mandelbrot set's a resource. Everything's a resource. Let's show you how that's done, just so you understand the details of this demo. So what I've got is another module over here, and I've got an address space set up. You see, I've got this. I actually start to read this code and think, well, there's a space. I declare a space. It's an address space. Inside that, I've got some file resources, and then I've got a mapping between Mandelbrot local with a real and imaginary part. And again, I've got a grammar for parsing. These grammars got to be rewritten because they're more complicated than they need to be actually. And when I ask for that, I actually invoke Groovy, and I call local Mandelbrot, and I pass through the real, imaginary, and the zoom factor. Okay, that's all I'm passing through. So that's my ground. Let's look at local Mandelbrot. What does it do? Like every endpoint. What are you being asked for? Give me the request. Give me the ZR. Give me the ZI. Give me the zoom. Create some stripes. Let's have 8 stripes. And let's create some handlers. And for each stripe, I'm going to construct a request to active Mandelbrot stripe. I'm going to pass through the ZR. I'm going to pass through the offset I, some steps, some width, some zoom factor, some iterations number. And then I'm going to issue that request for that resource, because that's the identity of a resource. It's that part of the Mandelbrot set I want. So issue that request. But rather than issuing the request serially and waiting for the response to come back, I just say, actually, I'm on a multi-core system. So I'll just issue it and carry on issuing more requests. And that one's going to go off and get serviced while I carry on issuing more requests. So in a loop, what I do is I just go splat, send 8 requests out, and I don't care. I'm going to let the system load balance those across the cores for me to compute that. So what I'm doing is I'm parallelizing the Mandelbrot set just by asking for it logically like this. Name for that Groovy runtime, so it doesn't use the local version. It's going to use the one that's over there in those servers. But the code is called res resources Groovy Mandelbrot stripe accessor, which happens to live just here. This is the internal detail of what's going on in that Groovy code. And down here, you remember that the Mandelbrot set is basically the distance in the imaginary set. So I'm going to take the imaginary set out. Let's just change the algorithm, okay? And now let's run that again.
Just out of curiosity, does this mean that theoretically somebody could write a request on their side and then force your system on your side to run some code that they've written on their client?
If you wanted them to, but obviously you've got to be very careful. So you have to have very careful constraints and the ability to put constraints on it. So what you can do is create very rich trust models through resource relationships, and that basically says, well, I trust, I'm going to establish trust or not to allow you to run that stuff or not. But basically, the ability to run code is not dictated by what's deployed on the server, but it's dictated by what relationship you have between address spaces. And that is a context that's established extrinsically, externally, by policies and enforcement rules that aren't part of the functional requirement of that particular task. They're another aspect that's decoupled. So if we go back and look at that view, when I take the imaginary part out, you see this frilly kind of Mandelbrot set. That's what it looks like without the imaginary numbers in it. If you've not seen that, that's what it looks like. Not a different pattern. And then I've got one more example here. And this one's kind of the clincher for us. If we look down inside here, what you'll see in the third demo is a request for Mandelbrot mount. And this actually calls local Mandelbrot. It's calling the same piece of code I showed you at the very top of the day. So it's actually calling Mandelbrot stripe here. So it's going to run locally, isn't it? Well, no, it's not, because what I've done, in my address space, I've put in place this round-robin load balancer, and it's set up with a configuration to point to that set of servers. Okay, and what's going to happen is that request for Groovy, that Groovy local is going to run local. It's not remote code anymore, it's local code. It's the same code I ran the first time. But when it issues a request for Mandelbrot stripe, each one of those requests is actually going to get load balanced into that server farm over there that's got the Mandelbrot stripe endpoint in it. So I'm going to fan it out and distribute it. So if I run that, what you'll see is the round-robin load balancer says, yeah, I'm connecting to that host, it's now up. NKP, it's timing out. It's it might run again if I run it again. Let's try. I think my connection's too weak. No, it's starting to work. I'm not sure I can do that demo. I think my phone is underpowered to do that at the moment. But what I wanted to show you was that you can put in place an architectural relationship in this space that says that the code in this space doesn't even need to know at all that it's being distributed. It's effectively the developer of this code doesn't even know that there's a relationship outside into the outside world. That you're fanning this thing out into a cluster. So it's exactly equivalent to that load balancer pattern that I showed you that the web can do. But now you're writing local code. It always looks like local code. It can be tested against local code. So you can have a local implementation. You can develop it all locally. And then you just put in place this one architectural hook, and it then just goes distributed. And then there's one other thing that I might be able to show you, but maybe I can't. It depends on the state of my system. But the other thing about this is, I go remote. Yeah, it came back. So I just made a remote, I just ran that remote demo for you again. And what happened was, it hit my cache on this side, because the cache is also coherent through the cloud. So this dependency model that we talked about, where you can accumulate knowledge of the dependency relationships, that now is spanning between the servers as well. And it knows that there's nothing changed on those servers last time it asked for those computations. There's nothing changed in the computation of this resource that I just made here, so I can just give you it straight on my cache here. Okay. If someone reset that server over there, then just like I did with the golden thread, 4 of those stripes would get changed. Okay, but the other 4 wouldn't need to be recomputed because I'd already got cache values for them. Came over the wire. If someone reset 2 of those servers, half the thing would be recomputed. But I can always have this coherence of the state of these systems, even though they're distributed now. So, God, that was a long demo, wasn't it? Right. That's the end of the story, really. The summary is, there's actually something very simple here. And the simplicity is that the web is a very simple system. It doesn't have any technological constraints in it. It's not a technology, it's an abstraction, it's a model. And so it doesn't matter what browser you use, it doesn't matter what server, it doesn't matter if you use Java or C# or Perl or Python or whatever inside the endpoint. No one cares. The relationship is between this requester and this information, this abstract set of information. So this thing can change, and this thing can change, and the system carries on working. Or I can intermediate, and I can hit and get the same representation back. And what we're saying is, those properties can be generalized, and once you generalize them and really understand that space and the mechanism that makes that space work can be used as the unit to create systems, then you can basically say, look, all of that can be hot deployed or changed or evolved at its own rate because it doesn't matter. I don't care what's inside those boxes. I don't care about the damn technology. What I care about is information. This is IT. It's not TI. The information comes first. But we put the T in front all the time. That's the problem with information technology most of the time. And of course, it also doesn't matter where the hell I put that stuff. So I can take I know that that's an application because I get used to these patterns and looking at it. I get a 30,000 foot view and I know that's an application. I can take that application and put it onto multiple sets of servers. And nothing in my architecture here needs to care or know that I took that architectural engineering decision, that change of location of the computation. Because it doesn't matter where you compute. It really doesn't matter. What you care about is the information, every single time. That is resource-oriented computing. And if you want to learn about it and play with it, then you can download NetKernel, and it's just a great toy. It's like doing Lego for a living, That's all I'm asking you to do. It's just great fun to put stuff together this way. Because rather than getting locked down inside this mungy, hideous detail, and locked inside this tyranny of APIs, you step up and you start to deal with larger lumps and simpler names for stuff and human readable things. And Chris is sitting in the back row, and he picked this up, 5, 6 years ago?
Something like that, yeah.
Yeah, and you just do this for a living, don't you? And it's just, he's got the easiest job in the room. All right, I can be contacted here. There's news, there's stuff, and so on and so on. But, you know, give it a try. It's a lot of fun. Now we should go to the pub, I think. Thanks, everyone. Thank you.